right, let's get started. Well, happy Valentine for those that are going on a date and not going on a date. Okay, so it's going to be a very romantic topic today. Dear to my heart, protein modification.
Oh my God, you're stuck.
All right, so okay, so today is my last lecture, so if I'm not done on time, bear with me, a couple of minutes. I might be done on time. We'll see how it goes. So we just want to make sure I finish the material that is relevant to your lab that you will do later on in the semester. So for protein modification, does anybody know why do we care or even want to modify a protein? Yeah?
If you want to make a protein more soluble, if you're trying to
Very good. Make a protein more soluble. Make a protein better digest. Oh, you were going to say that?
say that.
Sorry, I forgot about participation.
Yeah. I was going to say more digestible.
Okay, that's good. And when I say protein modification, what do I really mean? What am I modifying? Huh? Molly? Okay, the structure. So I'm modifying the structure of the protein, and we talked about last time how structure function affect function. So we're aiming to change the structure in a targeted manner. That means I want to make sure the protein is more soluble, or I want to make sure that the protein emulsifies better, or gels better, or is more digestible, or whatever is my target. So different modification, even with an enzyme, if we talk about enzymatic modification, even the type of enzyme and the conditions we use to hydrolyze will give us different structures and different functions. So there are so many different ways to modify a protein. Today we're going to talk about the two most common ones. This is very much applied in industry, and this one is being investigated for applications in industry. So chemical modification is ancient. By chemical modification is that you're chemically inducing a change in a functional group. Either you add a functional group or you block a functional group. But it's banned from the US because of the use of chemicals, and also the possibility of production of metabolites that could be toxins. So we don't care for it as much anymore. In physical modification, we mean, let's say, a high pressure a modification of a protein, pulse, electric pulse. So any modification that is physical that might impart a change in structure. Biotechnology is, yeah? The denaturation is a consequence. It could be a consequence of a physical modification, or a consequence of Maillard glycation, or a consequence of chemical modification. So denaturation is a change in structure. Okay. So biotechnology is genetic engineer. You can genetically engineer crops, for example, to have different essential amino acids. So if wheat is deficient in lysine, you can genetically engineer wheat with more lysine. So biotechnology, which is genetic engineering, is frowned upon by consumers. And it's more difficult to achieve in order to get a targeted change in the protein rather than any of the other methods. So, and technologies still appear and come, so we don't know what in the future will be in terms of protein modification. So the aim is to improve functionality, enhance nutritional delivery, and physiological benefits. However, whatever we use, whichever method we used, has to be safe. And that's why, for instance, chemical modification is no longer pursued. Okay? So we'll start with enzymatic modification. So common ingredients, protein ingredients, include protein hydrolysates. So when you hydrolyze, you improve the digestibility. For example, whey protein. So baby formulas, babies don't have very well develop digestive systems. So in baby formulas, if they're using whey protein, they use slightly hydrolyzed whey protein, so that it's easily more digestible or more easily digested by the infant. Enhanced bioactivity. So when you have a protein and you hydrolyze, you release peptides. Some of these peptides, depending on the sequence of the protein and where the enzyme cut, could be bioactive. That means have physiological contribution. Anti-inflammatory, antidepressant, satiety promoters, antioxidants. So it depends on what peptides you release. You might have associated physiological benefit. And with hydrolysis, you improve solubility, water binding, and other functional properties, but really it depends on the enzyme you use, on the degree of hydrolysis, and also the conditions you use for the hydrolysis. I have here reduced allergenicity, but to have a really hypoallergenic product, you really have to have very high degree of hydrolysis. That means most of the peptides are broken into amino acids, dipeptides, tripeptides, and it becomes a really bitter product and not very functional. So it's not really, you won't find a protein hydrolysate that has minimal degree of hydrolysis. 3 to 8% of the total peptides are broken that are hypoallergenic. In order to produce a hypoallergenic ingredient, you really have to have above 80% degree of hydrolysis. So in industry, once you hydrolyze, or even in the lab, if you're doing hydrolysis, you want to make sure that you inactivate the enzyme at the end. You don't want the enzyme to remain active. You want to control the hydrolysis and stop it when a desired change has been reached. So enzymes are inactivated, often in the lab setting or bench scale, or sometimes pilot scale. You thermally treat the solution with the protein and enzyme to inhibit or inactivate the enzyme. On a large scale in industry, often they use enzymes immobilized on membranes so that it's more efficient. They don't use a lot of enzymes, and you don't have to use thermal treatment to inactivate. So when we apply hydrolysis, it's very important to control it. So it's not you just put an enzyme and a protein and let it hydrolyze. You have to control it. You have to select the enzyme. You have to select the conditions. So it really has to be controlled. What you control first is the degree of hydrolysis. The degree of hydrolysis is a term that represents the number of peptides broken with respect to the total. So it's a percentage of peptides that have been broken, peptide bonds, that is. And the other aspect, so you have how much hydrolysis you're doing, the extent of hydrolysis, and then next is what are you hydrolyzing? That means you rely on the specificity of the enzyme. So here's an example up here. So if you look, the further one to the right here is a soy protein isolate. So you have different components within that protein isolate. And then here the second one from the right has been hydrolyzed with pepsin enzyme. This one, the third one from the right, has been hydrolyzed with, I believe, either papain or alkylase. Let's go with papain. So a papain enzyme has selectivity to these groups. We call them the conglycinin subunits. So you see them disappear. So that's a very specific, an enzyme that has specificity to certain regions on the protein, and it targeted these subunits. Whereas pepsin has specificity to glycinin subunits, and you see that they're gone. What you see here is different. You see peptides, smaller molecular weight peptides generated. So here at the bottom of the gel. Okay? So this is an indication of larger proteins broken down into smaller segments of the protein, peptides. But one enzyme selectively or specifically selected a subunit versus another enzyme that selectively selected a different set of subunits. So we'll give an example later on how that impacted functionality. So specificity impacts which subunits are being hydrolyzed and also functionality, and I'll show you examples later. Extent of hydrolysis can also be controlled. So we're controlling for enzyme, we're controlling for amount, and we can control the hydrolysis type of the enzyme and its specificity, processing conditions. So what's the time, temperature, and pH. So pH, for example, affect the protein charge. So by changing the protein charge, you might impact different sites in the enzyme accessibility to certain sites. So you might impact which bonds are more readily broken than others. So hydrolyzing a different pH, it's not only the optimum pH of the enzyme, it also impacts the structure of the protein, and therefore it impacts what peptides are released. Denaturation of the protein, here's an example of the impact of whether the protein is denatured or not denatured. Here we started with a native protein, so protein is not denatured. Here we started with a protein that has been thermally denatured. Same enzymes, we use papain and pepsin, but if you see here, we lost specificity. So the enzymes hydrolyzed non-specifically the subunits, meaning both proteins have been denatured, and the enzyme had ready access to the different binding sites. So you can see that the denaturation of the protein impacted how specific the enzyme can be. So what happens, these are general things that could be consequence of a hydrolysis. One consequence is you have increased solubility. And why is that? Because when you break a peptide bond, you are releasing a potentially ionizable group. You're releasing carboxyl groups, and you're releasing amine groups. So they're both potentially ionizable groups. So they will interact with water more. So basically you increase water-protein interactions. So theoretically, you're increasing solubility. The increased charge on the surface of the protein due to the increased ionizable groups also result in reduced polymerization when you heat. Because of charges, you have more repulsion rather than attraction via hydrophobic interactions. So theoretically, you also enhance thermal stability. Other functionalities could be enhanced as well, improving gelation. So by hydrolysis, you can produce peptides, we call them aggregate promoters. So depending on the enzyme you use, you might release peptides that are more hydrophobic, or hydrophobic groups are more exposed. So you can have interactions, protein-protein interactions, and as well as protein-water interaction, then you get better gelation. Slight degree of hydrolysis. If you have really high degree of hydrolysis, you actually reverse that effect. You have much more enhanced solubility and reduced gelation, because small peptides will not form a good gel. Okay. The other one, also depending on the starting protein and the enzyme you use, you might end up having a mixture of peptides with good balance of hydrophilic to hydrophobic groups on the surface. So having a good balance between repulsive and attractive forces will improve surface activity. It could be either emulsion or foam activity or functionality. So what I say is sometimes this is not the case. What I mean, it's not always you're improving solubility. Not in every time you hydrolyze, you're going to improve all of these, basically. So it depends on the peptides you generate. Sometimes you see the opposite effect. So let's look at this example. So here, we were targeting, this is an experiment we did in the lab, we were targeting changing the soy protein to release bioactive peptide and at the same time enhance solubility. So we were trying different enzymes to look at the different specificity of the enzymes and what we get out of that. We started with a soy protein isolate that has been produced in the lab, so it's native, it's not denatured. And then we subjected it to different enzymes, alkylase, bromelain, papain, and trypsin. And then what happened is we targeted only limited degree of hydrolysis, 5%, and then we inactivated the enzyme by boiling, and we released bioactive peptides. We measured that, and we established that portion. We looked at the solubility. We were hoping for either not affected, because this is really high already to start with, or improved. But what we saw is in every enzyme we used, we saw a decrease in solubility. So how can you explain that? From looking at the results and looking at the sentence above it. Megan? Yeah. So the heat treatment that we had to use, some of these are really thermally stable, so we really had to boil and 5 to 10 minutes to ensure that the enzyme has been inactivated. But then by doing so, not only denatured the protein, but enhanced hydrophobic interactions and disulfide linkages. Heat enhanced these two. But what's interesting is they all behave differently. So depending on the enzyme we used, the degree of reduction in solubility is different. So this tells me that trypsin produces a different set of peptides than alkylase would. Trypsin might produce peptides that promote aggregation rather than solubility. So this is to highlight specificity of different enzymes, the differences in peptides generated, and mind you, they're all 5% DH. So it's not only the degree of hydrolysis that matter, it's what are you producing. Yeah.
But there's probably a way that you can do this that wouldn't denature.
There is a way to not denature the protein, is that what you're saying?
Yeah.
If you use an enzyme that is thermally less stable, so we are testing a different enzyme in the lab that can be inactivated at 70 degrees Celsius. So using a different enzyme that would be inactivated at lower than the denaturation temperature of your protein, or better even immobilize the enzyme.
Because so you wouldn't be able to get this graph, but without boiling the protein.
If we don't boil, we won't get 5% DH. The enzyme in water is going to continue to hydrolyze, so we won't be able to control it.
Other than immobilizing, is there any way that you can stop the enzyme without changing the structure of the protein?
Well, that's tricky. Enzymes are proteins, and proteins are proteins, right? So you can change the pH, for example, bring it down to 2 and leave it there. The enzyme will be inactivated, but also you're hurting your protein as well.
So if you know the protein you're using your enzymes on, could you like engineer an enzyme that will go to a certain degree? Could you say, okay, I know how many active sites of this kind are on this protein, like so
On the end, yeah.
5%.
Yeah.
And you figure out like an enzyme that you could make up, even if maybe it doesn't exist, but you could like in the lab create it, and then that would go to like that percent.
I don't know how straightforward that would be, but I can tell you there's a lot of bioengineering that you can really produce what you want, but not necessarily have that clean-cut target. Yeah. Yeah.
How we control the 5% hydrolysis?
Very good question. How do we control the 5% hydrolysis? You do a lot of pre-trials. So we know the optimum pH and temperature of the enzyme. We always start there. And what we experiment with is the amount of enzyme to substrate that you add, because the less amount of enzyme you get less hydrolysis. Okay? And then you control the time. So you test different combinations of enzyme to substrate ratio, and you test 30 minutes, 60 minutes, 10 minutes, and see which one will give you your desired DH. That's a good question. Okay, good. So I told you I'm going to go back and tell you the impact of specificity on functionality. So here's an example by different group of researchers. What they looked at is the impact on gelation. In this case, it's gelation. So glycinin, these subunits can form a stronger gel than beta-conglycinin. This is known about soy protein. So these subunits are better emulsifiers. These subunits are better gel forming, depending because of their structure, the degree of hydrophobicity, the presence of sulfide groups that impacts, and the balance of charged and hydrophobic groups on the surface. So the characteristics of these proteins make this one better emulsifier and this one better gelling agent. Okay. So they did papain and pepsin hydrolysis, the ones I talked about. This is papain hydrolyzed, this is pepsin hydrolyzed. So looking at this figure, the RCH stand for reduced conglycinin hydrolysate. So reduced meaning this is the fraction that the conglycinin was hydrolyzed. And then the RGH stands for reduced glycinin hydrolysate. So it is for the hydrolysate that the glycinin has been hydrolyzed. So, and this is the control, which is not hydrolyzed, in this case the isolate. So you can see when they hydrolyzed glycinin, the gelation or the strength of the gel was reduced, whereas when they hydrolyzed conglycinin, it is a little higher, but I mean, it's not that impactful. That means that protein subunit did not have an impact on the gelation performance of soy protein in general. Whereas when you broke down the main component that elicits gelation, the gel properties were diminished. Okay. All right, so what you're going to do in the lab, you're going to use a pH stat method to hydrolyze whey protein?
Yep.
Okay. So are you familiar with the pH stat method? Does anybody know what it meant when we say pH stat? What does it mean, Lucy? Yes. Perfect. So by pH stat, making it, as Lucy said, you keep the pH static. So when protein is hydrolyzed, you are releasing carboxyl groups, so pH tends to reduce. So the pH will, as you hydrolyze and as you hydrolyze more peptide, the pH will go down and down and down. In pH stat method, what you do, you titrate. So here's where you put your buffer, sodium hydroxide. Here's your sample, and usually you have a water bath to control that, and you have a thermostat, and then you have the titration tube that goes in it. So what you do is, and then this is the pH meter, it measures the pH for you. So, and adjusts accordingly. So you will automatically, NOH will be dropped in as the pH starts to decrease. NOH will be titrated in to maintain the starting pH of your hydrolysis condition. Let's say it's 7 or 7.6 or whatever it is. So it will maintain it there. The amount of NOH that is added to maintain the pH, you use that to calculate degree of hydrolysis. So you use an equation that takes into account the volume of NOH that you've used, the normality of NOH that you've used, because if you have 0.1 normal, you'll use more. If you have 1 normal, you use less, obviously. So the normality is important, the amount of protein that you have, and then the dissociation factor, which is a factor you calculate based on the pH and temperature of your system. So there's an equation for that. And then the H total, which is the total number of peptide bonds in your protein. And this is unique to the type of protein. For whey protein, you have a number. For soy protein, you have a number. So you will enter that. Multiply by 100, it will give you the % DH, degree of hydrolysis. So you will perform the hydrolysis at a specific pH. You will be given a certain ratio of enzyme to substrate, and then a set time and a set temperature. And I'm not sure what enzyme you're going to use. Trypsin. Okay. And then usually we do that at 5% protein solution. So that's what you're going to see or do. Prepare a hydrolysis.
Can I add to that?
Sure.
I just wanted to say I haven't really had a chance to talk about the labs a lot with you. So this is what we will do next week. And this week we will prepare the base that Pam just mentioned. You titrate with sodium hydroxide. And the protein itself is in a buffer. So we will prepare the two reagents we need next week. I'll give a lab intro too, but I thought it would fit with that.
Good. So you produce that hydrolysate, and then you're going to compare solubility of that hydrolysate, emulsion, gelation, everything. All the functionality, you compare it to the non-hydrolyzed version of it. Okay. So I'm going to give you a practical industry problem and then a way to mitigate that in modification, by modification. So you probably heard me say whey protein is the golden protein for beverages. Did you hear me say that? Okay. So it is the protein ingredient that is most favored to be used for high protein beverages. However, there is a caveat to using it. It's great protein, but it's not shelf stable. It denatures at low temperature, and if you have high protein concentration in that beverage over time, denatured proteins are going to interact with each other and precipitate. So although it's a very soluble protein, but it doesn't have a long shelf life. And a short shelf life is not economical for industry, so they're always looking at ways to extend this shelf life. How can we make that protein stable? It's soluble, but then over time it sediments. Okay. So here's the model. So what happens, this is your beta-lactoglobulin, which is the main component of whey protein, and it could be the major one, more than 80% in whey protein isolate, let's say, that you get from ion exchange. So depending on the ingredient, beta-lactoglobulin might be the major component. So once you heat, it's going to open up, denature, and then expose your hydrophobic groups and a sulfider group. And then over storage or more heating, what's going to happen is hydrophobic interactions and disulfide linkages, aggregation and precipitation. So that's what happens over shelf life. So stepping back, looking at the beverages that are produced with whey protein, you have the neutral beverages and the acidic beverages. The neutral beverages usually are opaque because whey protein is not clear at neutral beverage, so usually you find those chocolate flavored, strawberry flavored beverages, so opaque, creamy drinks. But the acidic beverages are clear, like fruit juices, and they're desirable because they're clear, and they're desirable because the pH is low, so they are processed as acidic food. So you don't have extensive heat treatment, so the flavor is maintained better. So they're desired. However, you know, proteins are buffer. Bring those pH to this low pH, then you're going to end up with really sour beverage. If you have the pH higher, still acidic but higher, 3.5 to 5.5, your beta-lactoglobulin are forming octamers. So they are around the isoelectric point. They are not clear. They're aggregates. So that's why you need to lower the pH to lower than the isoelectric point, and then you get a clear beverage, yet you have a problem with sourness and astringency. So now we have several problems. We have sourness and astringency due to low pH, and we have a shelf life that is short. So two things that are problematic. So we can hydrolyze. So if you hydrolyze the protein, yeah, okay, you'll have better solubility. However, if you have high degree of hydrolysis to have really enhanced solubility over time, flavor challenges to bitterness. Or if you hydrolyze, the other challenge is you're breaking bonds, so you have amine groups and you have carboxyl groups, so you have even more buffering capacity. So that means you need to add even more acid to maintain a low pH. Then it's worse. Flavor is worse. And disulfide interchange can still occur. Once you hydrolyze, that doesn't mean then the proteins over shelf life, they won't polymerize. In fact, they can aggregate and precipitate by heating and over time. So hydrolysate, they found it didn't solve their beverage problem. So, however, something else can form or can improve the shelf life and solubility. And that brings me to the next one, which is deglycation, which is being considered in industry in several companies right now. It's not commercial yet, it's under investigation. Okay, so Maillard-induced glycation. So from the name, it's Maillard reaction, but it's really the initial step of the Maillard reaction, which is the condensation reaction between a reducing carbohydrate, a reducing end, the carbonyl group, and a reactive amine group on a protein. You get a series of reaction, formation of shift base, and then rearrangement, and you get the first stable compound, which is the Amadori compound. So this one is a glycated protein. So you have amine group blocked, and then you have a carbohydrate linked to the protein covalently. And then you want the reaction to stop. You just don't want it to go further into intermediate and final stages of the reaction. You don't want this complex reaction to continue into advanced stages. You don't want to have mutagenic compounds or even polymerization of the protein or browning or off flavor. So you really want to stop it at the Amadori compound formation. So how to do that is you control the reaction conditions. Okay? So you probably know that optimum, for example, water activity for Maillard reaction is somewhere between 0.5 and 0.7, where reaction happens more spontaneously, and of course you want the heat for the reaction to occur. So, and then of course you want the reducing sugar. So we look at these conditions and we go, okay, so we want the reaction to happen, but we want it to be slow, and we want to be able to be on control of stopping it. So we select less favorable conditions for the Maillard reaction. So we select temperatures that are not very high. We don't want the protein to denature either. So, and we select water activity that is less than the optimum. And then we select carbohydrates that don't have high reducing power. So DE values that are not really high. So you know what DE values, right?
I know what it means.
I know that you know. Did you teach them that? Or did they get it in?
They should have heard it.
So what is a DE? What's DE? Yeah, what does it mean?
Something like the glucose content,
Equivalent.
Get down from
So 100 DE is equivalent to glucose with the reducing power of a glucose. And then as the number is lower, that means you have larger molecule and less reducing power. So we use polysaccharides that are not very small and they don't have a high reducing power. Therefore, we can limit the rate of the reaction. And we target something we call partial glycation. That means you have, let's say, you have several lysine. Lysines are the most reactive amino acids. They have the primary amine in them. So let's say you have several of them. You don't want to glycate every possible amine group in a lysine, right? So we want to target partial glycation. That means some of these groups, not all of them. Okay. So what we expect to happen is when you block an amine group, you're basically blocking a potential positive charge. So the net charge of the protein will be more negative charge. So you will have a higher net negative charge. So by having higher net negative charge and a small sugar relatively interacts with water, then you are increasing the surface hydrophilicity of the protein. Great. By doing that, you have more charge, more surface hydrophobicity, the denaturation temperature will be higher. It will resist denaturation. And then because you have these bulky groups, there's steric hindrance. So they will kind of repel each other because of hindrance of these bulky groups, so you don't get disulfide interchange. And with that, you get better solivation. So you have better interaction with water over time. So here's demonstration that it really worked. Like I said, whey protein is very soluble. So starting with a whey protein that is soluble with and without heat, you really have really good solubility at pH 3.4. But that's not storage study, that's just now. We measure, we prepared it, we measured it, it's very soluble. However, around the isoelectric point, the solubility drops from about 100% to 4%. Most of the proteins fall out of solution. Okay, let's look at the glycated one. The glycated one has around 90% solubility or higher around the isoelectric point. That's because the net charge was higher. The isoelectric point shifted to a lower pH. So what happened here, why is this exciting? Because you can produce an acidic beverage, but it doesn't have to be 3.4. It can be 4, 4.2, 4.5. Then you need less acid. So you solve the problem of sourness and astringency. So it will still be acidic, but not necessarily too acidic. The solution can remain clear and not as acidic because you don't have to go down all the way to 3.4.
So why isn't this commercially available yet?
Because it's more recent, not well researched. I mean, it is researched now, but it's not as old of a technology as hydrolysate. So they're looking at feasibility, how to produce it with the cost. It always has to do with cost and efficiency.
More so on like producers, not necessarily the FDA will approve this?
It's both. So the producers need to find a way that it's economic to produce it. Second, they want to make sure that how they're going to label it. Okay? So, for example, producers are looking at using this technology in an ingredient that has already endogenous carbohydrate in it. Then they don't have to add anything, and it would be like a processing. So you don't have to put that on the label, how you process it to initiate modification. So if they go that route, then it's natural processing outcome. Good. So now we looked at what happened to the structure. We always have to link structure to function, right? So we looked what happened to the structure. We looked at the denaturation temperature. So the modified protein, the denaturation of BLG, remember this is a DSC thermogram. So the denaturation temperature shifted higher about 16 degrees Celsius. So we proved that by solubility around the isoelectric point, we proved that net charge is increased, and we proved that denaturation temperature was increased as well. And we proved it in a different way as well by looking at surface hydrophobicity. We're looking at the surface hydrophobicity when you heat at 75 degrees for 10, 20, 30 minutes, etc., 70 minutes. You see an increase in surface hydrophobicity of the non-modified protein. So the protein is opening up, is denaturing, unfolding, exposing the hydrophobic groups. Whereas the one that's being glycated, modified, you see a slight increase, but that's because you get partial unfolding, and then it maintains. So it remained more stable in terms of change in structure. Okay? And then at the beginning, the surface hydrophobicity was lower for the modified, and that proves the hypothesis of hydrophilicity will be higher on the surface. That's what we said earlier. And then polymerization, this is when the regular protein, not modified, polymerize after heating for 10, 20, same samples. You see an increase in polymer formation, The glycated, you don't see that polymerization. So great, that's excellent.
I just have a question. So how you were saying like the acidic, like the clear,
Yeah.
is less stable. When like over the summer right where they work on like muscle milk, like muscle stuff, and they were saying that there's a new product that's like protein water essentially, so it's obviously clear. So could that be like part of like this technology coming out or not really?
So they said it's stable for how many weeks?
I don't
And
know.
at what?
It just came out. We were like tasting samples of it.
Yeah, could be. Who knows? It could be that. It could be use of unique other modification technologies.
Yeah, I think it's called Isopure. It's like
Yeah.
the same thing. They have like sour apple and stuff like
Yeah.
that. And that's been around since like 2013 at least. Like that was when I first saw it. And I remember it had like a pretty long thing. Like I was worried about like if I had to store it in like the fridge or anything. And I think it said if like unopened you could store it for a couple months.
Couple more. Pretty good. I will be very interested. What's the protein percentage?
I don't know.
It's like it's a decent amount because we were looking at it as a similar product to like the muscle milk shelf stable chocolate.
I will want to look into that. That's cool. Okay, so what will be done for you in the lab, and I believe they won't glycate themselves. They will be.
I haven't decided yet. Maybe they will.
So is it going to be whey protein hydrolysis or isolate? Whatever. So an ingredient, whey protein isolate or hydrolysate, is going to be mixed with dextran in a specific ratio, and we put them in desiccators usually, and the water activity would be controlled salt solution at 0.49. Okay, so in industry, that's another thing what they're looking at to answer your question in terms of efficiency. Of course, they're not going to use desiccators. So looking at ways to incubate and glycate either in a continuous manner or using chambers, humidity chambers, large scale ones. So looking at feasibility of that. Okay, so in the lab we use desiccators with the salt solutions, and not me, that's one of my students did that. And then they're incubated at different times, and samples will be taken out so that you can measure rate and extent of glycation. I don't know how many samples you will be producing for them.
Ideally, one for each lab.
Great, okay. And then the way we determine that if glycation occurred is a semi-quantitative method, which is really looking at absorption at 304 nanometer. So you prepare your solutions at certain concentration and you measure at 304. The absorption is correlated to the amount of Amadori compound. So usually your control, you would run a control alongside with your glycated sample. Control does not have your dextran added to it. And then you would measure and determine which point has the highest glycation. But at the same time, you have to take into account browning, because we don't want the Maillard reaction to proceed further than the initial stage. So we monitor browning. There is another test we monitor is fluorescence that monitors intermediate stages metabolized. You're not going to do that in the lab. So we look at browning at 420. You can also look at browning by doing the color, the LAB. Are they going to do that? No.
Not for this assay.
Yeah, for something else. But the purpose is to really select which time point gives you best glycation, extent of glycation, and lowest impact in terms of secondary metabolites of the Maillard reaction and advanced stages. The next assay that you're going to do, it's an OPA assay, which is, it measures the extent of free amine group loss. So it's basically OPA reagent react with free amine. So the less reagent reacts, that means you have more amine groups that were blocked by glycation. So you would also determine that over different incubation temperature. You calculate, there is, you run a standard curve, obviously, and a set of calculations you run in that to determine percent loss of free amino groups. And then you would identify which sample point gave you significant reduction in amine groups, no browning, and that would be the ideal sample that you would proceed with. So I'm going to spend the last 5 minutes going over, I'm not going to keep you longer, so I'll be done in 5 minutes, to go over the protein ingredients that you'll be working with in the lab, just briefly, because I think you'll be given unknowns, right? And they will have to figure them out, or no? Based on the gel.
Talk about that. No, I will
Okay. All right. So,
They have an unknown starch sample.
okay. All right. So there will be a casein protein, a whey protein, an egg protein, and then soy protein, and then pea protein. That's the different proteins that you're going to work with, but you're going to hydrolyze whey protein and glycate whey protein. Okay. So the sodium caseinate, usually we run a urea gel, but in the lab you're going to run a regular SDS page. The reason we run urea gel is you'll be able to differentiate alpha and beta casein because they're very close in molecular weight, as well as kappa casein, you'll be able to differentiate. Okay? Whereas with SDS page, they will migrate a little differently than globular proteins. They will seem larger than the globular protein because they're open structure. So they're open structure, and then we're going to compare their functionality in terms of emulsification, for example, to different proteins because they're supposed to be the natural emulsifiers compared to other proteins given their open structure and the balance between hydrophilic and hydrophobic on the surface. The next protein, this is how it looks on your gel. When you run the gel, you have the two major proteins, alpha-lactalbumin and beta-lactoglobulin. So they are only differ by 2 kilodalton. This is a 16 to 18 kilodalton depending on the variant, and this is about 14 kilodalton protein. So you'll see them, they're really way down because they're small globular proteins. And then you're going to determine solubility and the impact of heating on the solubility, hoping to see something like that, that they remain soluble even at the isoelectric point without heat, but once they're denatured, then they will fall down in solubility around the isoelectric point. So hopefully you'll be able to see that in the lab. In soy protein, it's more complex. So you have much more subunits in soy protein than whey protein, for instance. So you'll be seeing, so you won't be hydrolyzing. So you're just going to be seeing SPI that looks like that. And then here in this, we ran standards so that we know what the different subunits are. Are they going to be soy protein hydrolysate? No. So like I said earlier, soy protein have two main subunits. The 7S is a better emulsifier, is better for emulsification, and the 11S, which is the glycinin, better for gelation. This is, we looked at the emulsification capacity, we talked about that last time, and stability. Emulsification capacity, how many grams of oil 1 gram of protein can emulsify. When we hydrolyzed with pepsin or alkylase, we increased the emulsification capacity, but when we looked at stability, you can see the one that has alkylase hydrolyzed has much lower stability. Alkylase hydrolyzed beta-conglycinin, the 7S. So when we broke it down, you lost stability. So that confirms that we saw the impact of hydrolysis of the glycinin fraction on gelation. And if you hydrolyze glycinin, gelation goes down. Here we saw the impact if you hydrolyze beta-conglycinin, you see a reduced emulsification property. To wrap up, okay, just wrap up question. If a protein is modified, in this case, glycated protein or glycated hydrolysate, what do you expect to happen? Peter. Improved thermal stability, that's one. What else? Anything else? Yes. We have good solubility, I would say, over a broad pH range. Okay. What did you say? Did you say improve or reduce? What were you going to say? Improve?
Yeah, but, maybe reduce.
It can go both ways. So the research that actually showed reduction in digestibility if the carbohydrate is large, and if you glycate a lot, more than partial glycation, then you're really hindering the enzyme from getting to the binding sites. But in the study that we've done in the lab, actually we saw 9% improvement in digestibility because glycation caused partial unfolding. Okay, bear with me for a minute. It depends on the carbohydrate they use. You can actually enhance other functionalities, not just solubility. Okay. So hydrolyzed protein, that's the last bit. Off you go. Molly?
Would it have reduced overall functionality?
No. You would hope that is the opposite.
Have good solubility?
Again, I would say yes. Depending on the enzyme that you use, you can have any improvement in any functionality. So it depends on the enzyme and the peptides you produced it.
So it's glycated and it's decreased surface area.
Was it here?
It's on the other side.
Okay, yes. Yes, so if you hydrolyze, depending again on the enzyme that you use and the proteins that are targeted, you can enhance any of the functionalities. All right, we're done.